You can all celebrate the end of a very productive and enriching program. But we'll have the 5th lecture by Tilman.
Yes. And thank you for coming again. Now it works. Thank you. Yes. Yeah, thanks for coming again. I know you're tired, because I'm also tired, and you had like an entire week more than I did, and like, I had 5 lectures, and I don't know, you had like 35 lectures. So like, okay, I see the problem. But yeah, thank you for coming back. Today, we are gonna do our last part of machine learning. So remember, like, I started with an introduction, like, about networks and uncertainties, my favorite topic. But classic application would be like, classification, like, basically saying QCD jet versus top jet, signal versus background. Second one was like, what us theorists, like, where we're concerned with is like simulations. So there's an entirely different architecture. It's called generative networks. Networks where you basically throw random numbers into the network and you produce a density in phase space, for instance. And the last part is, I think as it should, how do I measure stuff with networks? Like, we haven't talked about measuring stuff yet, right? We have talked about classifying, we have talked about simulations, but we haven't talked about measuring, so I'll talk a little bit about measuring stuff. Measuring stuff in networks, like, there's different ways of doing that, so I will talk about measuring stuff using these generative networks, and you'll see why how they work. But what I'll try first is, like, because I will use these generative networks in a very special setup, I'll start again, like, with the generative network just wrapping up a few things, and then we'll start move into, like, the special setup of exactly the same generative networks, if you think about it, to measure stuff. The word you need to know, like machine learning, in the machine learning community, when people measure stuff and, like, they want to like be fancy, they call this inference, right? And if you then call this interference, then you look really silly. I mean, like, it's inference. Inference is a fancy word for measuring stuff. Okay, and we use these, like, networks for that. But let me, like, briefly before we get there, like, just remind ourselves what I did. We had, like, these normalizing flows. Flows, or what we call INNs. INN networks. And we use them to generate events, right? TT bar, like, So what we always do with these networks is we try to reproduce a density in multidimensional phase spaces, which in one dimension, I'm just trying to reproduce roughly, like, figure 52 here, and this is on page 91 in the notes. So it has 4 panels because it's a money plot, and you're not supposed to actually, like, understand it in detail, but it's supposed to look like cool, complex, and include a lot of information, and that it does, I think. So in the top panel, you have this kind of distribution. And this is, I think, we did Z plus jets, so this is PT of, like, jet 1, of Z plus jets, right? So, and from the form of the shape of the distribution, like, it's a PT distribution. You don't know of what, but some kind of PT distribution, because that's how PT distributions look, and depending on how powerful your collider is, this is either 500 GeV or in our case 150 GeV. Doesn't matter. It's a PT distribution. And now I want to use those, and I told you, like, that one of the big challenges, like, with these generative networks is when you go and talk to the experts. You go, like, to Göttingen and to Steffen Schumann, or even worse, you go to Frank Haus in Durham and show them that. And then they, like, first response is, okay, like, how sure are you that this actually works, right? And, well, then there's 3 questions I can ask. The first one we took for granted, but we should think about this for a second. And that is, how do I know that my neural network, which I introduced in the first lecture as the perfect interpolation tool, doesn't just interpolate away features? Because the network, by being the greatest interpolation tool that we have, is going to be super eager to get rid of a feature. And we know, like, from the JSI, that sometimes, like, narrow features are important. Like, otherwise, like, if you don't see them, you don't discover anything, so that's not so good. So, like, what you do is you want to have all these mass peaks properly mapped. So how can I do that? Well, mathematically, you cannot. The network learns what it learns, right? And you can look at the training data. You can keep comparing to the training data and say, like, and I'm missing it, and so on and so forth. But there is that's part of the training, and like, it's difficult, and especially when once you have trained a network, you don't want to deal with the training data again. But the idea is that the training data is training data, and then it's gone, right? So something you can use, though, is that generative networks with these estimate a big density, right? And that's quite a task for a network. Classification networks or discriminators, like for the GAN, right? They estimate just one number probability map, like, a scalar field over your phase space. Much easier to learn, right? So you could use the discriminator. And remember the optimal discriminator. I think I had this on the Blackmon discussion yesterday. The optimal discriminator, we had that, like, yesterday was, had p data divided by p model plus p data as the optimal output, and that's, that's a value between, like, 0 and, well, 1/2, right? Any case, when you take that discriminator and you build an object that is d divided by 1 minus d, right? Then this will give us p data here from the d. From the 1 minus d, it will give us, like, p model plus p data minus p data divided by p model. And the numerator cancels, right? So this combination, which I called conveniently W, like weight, right, is constructed out of a discriminator that I can train. You train this, right? You train this either together with your network, the generative network, or independently, and then you can like construct this function out of this D that the network encodes, and then you can look at this. How that behaves in your phase space, right? And then you get some kind. So that should be 1, right? If everything is good, if it's 1, it's 1. And you look over phase space. So you look over the like n-dimensional phase space. I can just like write this for this phase space here. And what you see is like it behaves like that, and it goes a little like that. I told you that before, right? I mean, this is typical. So like it looks fine. If you have enough training data, you're running out of training data, there might be a systematic deviation. If you now scan your like phase space for these weight values, and you find deviations from 1 which are significant, like whatever, like your target of precision is like but like smaller than 0.5 or like larger than 1.5, you will find phase space regions where this network didn't do well. So this is controlling the network, right? That's just control. This is not actually an uncertainty, because in normal, like on normal tools, we don't think about it that way. But if you think it's the first thing you want to do when you like check the uncertainty of like of your network is to make sure it gets all the features right. Only then does it make sense to ask the question, how precisely do you get it, right? Because if you don't get anything, well, yeah, don't even bother asking how, like what the error bar is, right? So, and that's easy to do. Like, we did this, like, you can try this. Everybody can do that. It's essentially using a normalizing flow and then being inspired by a GAN. If you want to work on an open problem, by the way, try to, like, build a GAN-like, structure where you train together, like, you train the generative network and there's a discriminator. We tried that, works okay. I don't think this is a solved problem. Okay, the second part that is something, like, that I introduced in the first lecture, and then again yesterday. So this is here W. Then what you do is the BINN here, the Bayesian network over truth. Right? This is going to give you, like, again, like, some deviation here, right? But it's probably the same as here. But more importantly, it gives you an error bar. Right? I mean, so it should look like that. So now, if you have all features in, it makes sense to ask the question, how well do I get this underlying density? I derived that for you yesterday, and that is the uncertainties. Now, the uncertainties that we encode here in these like networks for generative networks are of a certain special kind. Like, you know, what we have shown, like what I showed you, typically is uncertainties related to lack of training data. But that's not the only uncertainty. Imagine you're training your network on Monte Carlo data, right? And somebody tells you, some of these loop people tells you that there's a large logarithm. Like, you know, in some tail of the distribution, the density that you get from the Monte Carlo data is actually quite uncertain. But I don't know what that is, right? I mean, a way to, like, you know, write this mathematically would be that you have an uncertainty on the weights or the densities. This is, again, the similar weight here, where somebody says, okay, the event weights in the tails are for unweighted events are of order 1, but if I like you know this, they give my central density, but you know I should consider something like like PTJ, like you know normalize it to whatever, like some number on GeV or something like that. So you have an uncertainty that increases with PT of the jet, for instance, the leading jet. That could be a large logarithm times the value A, and that A could be in some range. And like now, a theory uncertainty would tell you, well, that value of A should be in the range of, I don't know, like, you know, -3, yeah, could be negative, like, you know, -3 to 3 or whatever. You know, some range. Or just upwards, I don't know, like, you know, something, so this is like that. This is how you would want to incorporate a theory uncertainty, something that you know in the training data you can't predict very well. This is quantitative, like, you know, this is the kind of uncertainties, theory uncertainties that we always get, right? How do I incorporate that? Well, normally, naively, from our classification and task and from our regression task, we would say, okay, like, you know, just screw with the training data, like move it up and down, like, you know, and induce this kind of noise term, and then you know, something is going to happen. You can do that here. But you see, if you use this, the training data, and you to communicate this, and you just like you know move it around, what's happening? There's one big difference between like generative networks and like so it's a classification network, and that is a classification network. Remember, has labels, and you know what the labels are, right? Or like the supervised, so you have the percentiles, and I told you that we can smear those labels, right? Here, the density of these networks that you learn from, you don't have. Like, you know, they're actually encoded in the data set. So strictly speaking, all of these, like in the like, you know, formal like language, all of these generative networks are unsupervised because the underlying phase-space density is not explicitly known, it's just encoded in the data set. So like, you know, if you know screw with the data set, you might just make it harder for the network to learn stuff, and then you keep your fingers crossed that, like, you know, the Bayesian network will pick up that trouble and, like, you know, increase this uncertainty here. But then when you start to like, you know, communicate this, like, you know, like through correlations in other phase-space directions, this becomes very, yeah, not super reliable, I'd say, right? You can probably, it'll work to some degree, but, like, you know, I wouldn't be sure. What you can do instead is you can do something that's much more straightforward, and you can say, okay, let me generate my data set, my distribution here, and replace my model density here, like what I normally have, P model of x and theta, and let me, like, you know, modify my training data with these parameters of A, but let me include the parameter, like, you know, let me give this parameter of A to my model when it learns. So what you're writing is now, you're replacing your model density by x given theta and A. But you're basically saying, like, you know, I'm giving A to my model, and then I get a probability space, phase space, like, you know, distribution as a function of x given my network parameters and given this parameter A. So that's you're introducing this thing as a condition. right? But now you have given that as a condition. Now you talk to somebody who thinks about these things more formally, said like, but this is a conditional probability. Like to actually cover that, like, if I know what the distribution of A is, I know this, I know A is in between -3 and 3, well, all I need to do then is I need to say, like, have a distribution of P of A, sample that, and then I get the right output because I can sample over this like conditional probability. Then you sample this like with a probability, and you get the correct probability where the condition is removed. This is like simple conditional probability, right? So what you do formally here is you go from an INN to a conditional INN, CINN. Very simple if you think about it, like now driven by an uncertainty, like that's a real life problem. We have just like introduced conditional networks. Yeah, and what you get here is like typically we only move this up here just to illustrate it. So what you find is that you find like for different A's you get like different lines here. For each of these lines you get a Bayesian network, and then you can decide if your variation with A is actually significant given your Bayesian uncertainties from here, and you'll find if it is significant, then you want to sample over those A's, and you get that theory uncertainty. What's important, you get this now through correlation through the entire phase space. Right, so this is the theory uncertainty, or systematics, generally. Mathematics. I'm one of, yes? Hmm?
What is being called?
Oh, this is the PT of like, a jet.
No, yeah, what is on the y?
Oh, this is A in our case, like, this is like A. Here, this would be A small, and this is like A, this is 1, 1. Actually, in plot, I moved it 2, 3. Lines?
But what are the quantities? Sorry,
Oh, this is like, this is like, this is just network over truth. In that case, because I have uncertainties, it's a BINN over truth. Sorry, it's the same as here. Just for different values of A. Sorry. Yeah? Okay, so that was like, an introduction to like, a new network even. I mean, if you think about, because we're going to play with that. Very, very physics motivated. Like, I want to learn like phase-space densities under some condition, and that condition I can play with. Yeah? Okay, and the trick is you move from an INN to a CINN. The nice thing about that is if you think about it, you can now look at like, all the formulas, the loss functions, and I mean, you look at them and nothing changes, right? I mean, you include like, in your like, P model, P data, you just include this A everywhere, and I mean, you can go through the entire derivation of the loss function, and nothing really changes. So like, the only thing is you need to give the network A as an input when you train it, right? So like the A is a feature of the training data, or the modified training data. So every time you sample, like, you need to make sure that the network knows the X distribution here of the data or model distribution and A. So you have like, enhanced your space. Okay. Now that like, we know what a conditional network is, let me ask a different question which we can then use, for which we can use the same network to sort this out. It's a very different question. So like, this was just introducing, we can have these conditional networks here. I can leave this. So different question is, we have a forward simulation. We always simulate things forward. We're thinking like, for instance, you're simulating from like, as I say, you put in Lagrangian, and then you like calculate the hard scattering. Then you add the shower, or like QCD radiation. Then you add like, hadronization, which is a pain in the ass. Let me not write about this here. Then you add like, a detector. And then you get events. Right? This is my favorite little line here, like, what we simulate. And we always simulate forward. So like, we'll always like, take simulated events from here to here, and the experimentalists compare them like, with real events observed here, and then they do like inference. If you think about it, that's probably the best thing you can do if you know exactly what you're doing at every single step here. Weaknesses of this methods appear when, for instance, like somebody says, yeah, I can give you like a through-loop calculation of the PT of Higgs plus jets, the PT of the Higgs, but unfortunately, I can only do this kind of here. And like because the Sherpa guys haven't gotten around to put this into like into of their Monte Carlo generator, and the MATGRAPH guys said you're crazy, right? So like this happens. I mean, actually, it happens. And so okay, then relying on the forward simulation cuts into your precision, right? So you have to work hard to like get everything down to here. Okay, we can deal with that probably. Like just work harder. Another question though is, somebody like takes I don't know, like something we did like in the past. Some people like look for events with very, very high multiplicity because they're looking for little black holes, right? Very, very, very many events. It's one search. And then you say, okay, fine, like there are no little black holes, check. Like I didn't know that before. But like, analysis is done, there are no little black holes. However, this analysis, high multiplicity analysis, you can test a million things with that. You can test, for instance, the way like, higher dimensional operators coupling quarks and gluons to each other, right? I mean, because this is mostly jets, and you can just calculate this, like, the changes the way they interact. You can look for anomalous triple gluon couplings. You ask somebody, what do I want? Well, I want an event with as many jets as possible. Okay, so like, we have that. Unfortunately, it's a search for little black holes which don't exist. So like, what do I do? And then said like, yeah, we can do the analysis. Like, if you give us blah, blah, and that's forward. And then you can't do it because, people don't get around doing it because the next run hits and like, it's not going to happen. So I want a way to like recycle an analysis and say like, fine, I'm a theorist. I can go from here to here, to here, to here. I cannot go from that one here. I can't do this because that's unfortunately detector simulation owned by Atlas and CMS. So what if I go here? If Atlas on CMS would give me results not for PT of the leading jet, but for PT of a quark coming with a hard process, I could actually do the rest of the analysis myself. I don't need anybody. I mean, it's not going to be great, but like, I can do that. Cannot do this. Okay, so that brings us to like, a very like fundamental question, and that is, why do we always simulate forward? And that brings us to conditional INNs. Because if you think about it, what are we doing here? When you look about like, putting in the detector, we are calculating on our forward simulation. Forward simulation is essentially giving me phase-space distributions at the RICO level. I call it RICO, like detector level is RICO, like of X. It's a probability distribution of X RICO, like reconstructed phase space, given a certain event before RICO. Let's call that parton level, right? It's a little bit of an abuse because there's showers and stuff has happened, but essentially that. Forward simulation does exactly that, right? That's a conditional probability. You see why I try to introduce conditional networks first, right? So I can simulate that. As a matter of fact, we always simulate that. We usually don't talk a lot about this, about the fact that this is conditioned on X parton because we run the whole thing through from here and then we forget about this. But strictly getting from here, from here to here, right? So this is forward. I compute that. I compute a probability distribution in reconstructed phase space given a certain parton level event. So and I have a model for this, and I can do that, right? Detector simulation. Now think about it. What I want here is, I now want to it's called unfolding in the technical experimental language. I want this the inverse direction. I want an inverse distribution. So I want the inverse direction where I get X parton given X RICO. Right? That's what I want. I want now for a given observed event, I want a probability distribution and pattern level phase where that might have come from. Once I have that, I can run this entire thing myself. Right? Ideally, I want this event by event, a minimum amount of probability distribution. This is like the fundamental, idea behind unfolding. It's called unfolding. Experimentalists call this unfolding, detector unfolding. Okay, so what I'm doing is I'm simulating conditional probabilities. Now, if you do this with Monte Carlo, in principle, you see mathematically this is a totally symmetric problem, right? It becomes, by the way, it becomes asymmetric if you want it deterministic. If you want to know which exact, which exact pattern level contribution comes out of a RICO level, event exactly without a probability distribution, well, this is not poorly defined because there's some stochasticity, and a stochastic system I can't invert because, I don't know, there's no deterministic, right? I mean, the link. So it's important, this only works on densities. It doesn't work on, it doesn't work on individual events. But there's nothing stochastic, so it's actually what people call an incomplete inverse problem, technically, what people call that, right? But it's well defined at the pattern, at the density level. So, okay, now I think it's generally known that using our classic Monte Carlo tools, you can't do this. Mathematically, you could, but our Monte Carlo tools are not particularly good at that because they are heavily tuned to get this direction here super fast, super efficient, right? They're really good at it, right? And essentially, they have kissed this goodbye. So structurally, you can't just do that. It's not, there's no way. People are doing this, right? But what you typically do is you bin the data and then you look for bin migration, you shape these distributions. It's super hard work. There's lots of nice work on that, but if you buy the more statistics community in Atlas and CMS, where they write this all out, but in practice it just doesn't work with the standard methodology that we have with Monte Carlo. And I want to go into the details why that doesn't work. All I'm going to say is that with machine learning it does work, if you think about it, because now imagine I have distributions. So what do I need as input? Well, I need some kind of distributions where I have pairs of events. So my training data, my training input, training data, our input is pairs of events. Right? So it's X parton and X RICO. X parton, X RICO. I mean, this is how I generate these things. As I said, this is a stochastic generation, so I shouldn't expect to get more out of this than densities, but I have those, right? I have events, I have a forward simulation, I have pattern level events, I have a forward simulation, the forward simulation gives me RICO level events. It gives me it picks probabilistically sampled, it picks always one on the other, right? So you have encoded these pairs, right? And the pairing of those relates the two densities to each other, statistically, if you add enough of them, right? Okay, so then let's look at our network. So I want somehow a network, my conditional INN network. I want to train this on a model, or to give me a model that now gives me the probability distribution for my thetas that describes the combination of these events and in their relation, these pairs correctly. That pairing, right? I want to describe that correctly. So what I do is I take the expectation value here, and I'm sampling, that's important. I'm sampling from P parton distributions and P RICO distributions in pairs. So now I have the original network, I have added the additional condition, just like I did here, right? But I also changed my loss function slightly because I want both of these x's here, both of these x's as conditions. So like, I want a network to describe the mapping of the two onto each other. And this is like, the one way you can write this. Right? And this is your loss, so you're like, you minimize the loss, which means you maximize the likelihood, the log likelihood of your network parameters theta to describe these two mappings to each other. Okay? Now, if I have a network that's trained like this, right? What I want at the end of the day out of this network is not that probability. I mean, like, I want to minimize that probability, but you see what I want are these two, like, likelihoods, like, if you want. So, like, I want a likelihood, so, like, theta would then, like, if it's a network description, theta would appear here on the right-hand side, and I want the probability distribution of either x reco given x parton, if I do a forward simulation, or x parton given x reco from this probability distribution. But I know how to get there. It's called Bayes' theorem. Like, I can translate them into each other. Like, if I train that probability distribution, I can just as well train, rewrite this using Bayes' theorem, which, is universally true. Like, that we don't have to argue about that. So, like, I get, like, the likelihood out. So, like, how do I do that? Well, I write this. So what I want is that one, right? So let me, like, write this one here. So x parton. Let me choose xp, otherwise, like, running out of things. Given x reco and theta. So what I have done is I have used Bayes' theorem to exchange parton with theta, right? Okay, and then I have this log here. So, like, I can add now plus log. Let me just move this up. P parton, roughly P reco, matching P reco. I have that log here. So, like, the first log I need to add is there's always x reco here on the right-hand side. I never do anything to x reco. That's always around. So, like, what I need is I need to complete this theta here. If I have a plus here, so it's that. I must check because, like, with Bayes' theorem, it's always very embarrassing if you get the signs wrong because then it doesn't work. Okay, minus the other log around. So, like, this is p of x parton here on that right-hand side, exactly this. Given theta and, x reco, sorry. X reco. Okay. This is just the prior and the evidence. And this is p parton, p reco. P parton, p reco. Training is the same. I just changed the math. Right? I just wrote this. This is just Bayes' theorem. So this is like, you bring that to the other side, which means you do the integral over condition over parton. You get rid of that. You combine these two. You get rid of this theta. So on both sides, you get the same condition probability. Okay, now let's look at these different terms. This one here, there's no theta. This is like some, evidence, right? We know this, it happens, but it doesn't have theta, so we don't care. So it's part of the Bayes' theorem, but not part of our loss function. Second one, so that we can go. We can ignore it in the training. This one here is interesting because that's log p of theta given xr, but remember that I'm also sampling over xr. So, once you have the sampling done, this XR condition is going to be gone because you're doing exactly that. You're sampling over your condition. Sampling over condition gives you just P of theta. So this thing here is P of theta. That thing here, I should write this again. So this is minus log P of XP given XR and theta. This is my, learned on pairs plus log P of theta. Right. Wait, and I should always, this is always here like a p-model distribution. I should just address this is as always p-model. Okay, yeah. This is some kind of a, some kind of regularization that gives you how tells you how your network distribution, network parameters should be distributed. So technically that's part of the loss function. in practice, it doesn't do anything to the training of your network. So now you look at it, and we had, like, by training on this probability with the right, like, choice of, like, moving things to Bayes' theorem, we got exactly this. Right? So I can train a network to give me exactly that mapping. This network, now we go back to, like, the INN. That's described by, like, function G. And, like, we can write this down, but, like, so that means, like, so, like, you introduce this function G, and then I need to just see, yeah, about the generative network. So, but let me just draw the architecture to remind ourselves what this network does. Remember, these networks, what they do is they map random numbers, this generative network, random numbers onto something, and that something here is on the left-hand side, so that's X parton, right? So you have X parton, and you have random numbers, right? X parton, and you have random numbers. And this is your CINN. That's your network that you use. I'm using a generative network from R to X parton, which is, like, just encoded here, right? Okay, and we can call that function, what did I call this in this direction? G. And G of R, or G theta of R, that was our old convention, right? What I train as a condition from the outside is actually reconstructed events. This is a conditioning. So condition means it's information that I give to the network training, to the loss function, but it's not related to it's not mapped by these two things. Like, I am mapping random numbers to XP given XR, which you think about is exactly what's written here, right? In the easy example I gave you, I gave the number, the deviation in the parton level phase space. That looked simply fairly obvious that you can do this. This is really exactly the same. It's just a little more, like, unexpected, right? So okay, so you train this on detector level events. Detector level events here. Then here you give it the parton level events because you need to sample on both of them in parallel. You make pairs of them. So you give that piece of information to the network, you give that piece of information to the network, and you train the network to go from random numbers to parton level. That's what you do. This is what the INN does. One thing important to recognize, when you use these invertible networks to generate, like, or to solve inverse problems through generative networks, the fact that they're called INNs, so, like, they go both directions, has nothing to do with the task of the two things that, like, you're combined. It's really important to remember. Like, you could try to, like, use an INN to basically map these two phase spaces onto each other. But then there's nothing stochastic, and we know that then that problem is not actually well defined, so I can't use it. It makes no sense to ask that question if you want. I mean, you can keep your fingers crossed and hope for the best that will work, but it doesn't. So the important thing is, like, to recognize is that I have a network that is a generative network that generates R into parton level events back and forth. The fact that that goes back and forth at this stage doesn't really help me a whole lot, except that I can do Bayesian and so on and so forth, right? But the conditioning is the important part. So the conditioning is now that I learn the distribution of parton level events under the condition of a certain RICO level event, right? So I have a certain event that I observe here, and I have an inverse simulation, and I get a parton level probability distribution in the phase space. And what I use for that is the absolutely standard conditional generative networks, right? One side remark, you can do the same thing, you can try to do the same thing with a GAN, right? The only problem is when you look at the generator loss of the GAN, it's actually not a probability generator loss. The naive GANs don't have a probability distribution, which means you're not guaranteed to get actually the fully calibrated probability distribution in phase space. You're going to get some distribution that you can try to calibrate if you want. Again, fingers crossed. The advantage of the INN, or the normalizing flow networks, generative networks, is that their loss function is a probabilistic or like likelihood loss, right? So I can play Bayes' theorem here. So I train the network on that probability to describe these pairs, and Bayes' theorem tells me that that's totally equivalent of like, training a network to get the distribution I want. Yeah? Really crucial. Yeah, there's a lot of discussion, like, on that, like, it's a lot of, yeah. Initially, that looks like a little magic, because our field has been used to the statement that this is something that is maybe or maybe not possible, but actually in practice it's certainly not possible, and so we shouldn't even try it, and so on, like, a lot of reasons. So, like, when you like then pull out these neural networks and said, like, my neural networks can totally do that just fine if I train them on the right objects, namely these pairs. You train them on here. I get a totally fine, like, inverse simulation, just the same way I get the forward simulation, right? It needs a little bit of thinking, just 1 second. It needs a little bit of thinking that, why this is actually, in terms of the conditional probabilities and our network training, why this is really equivalent, right? If you wanted to train the network, by the way, to go the forward direction, I mean, so you can do the same thing, right? I mean, you just pull the other way around, and like, you have to be a bit careful with the sampling and so on, but you can do the same thing. It doesn't matter. Like, I'm starting with the probability here. Like, which one of the two distributions I pull to the left? Your choice. Totally symmetric problem. There is a model, and you're training on paired events. So there is a model dependence on that. Like, there is a model encoded in your pairs of events. But that model exists in the forward direction, it exists in the backward direction. Right? So stochastically, you can invert this problem. Not individually, like, not deterministically, but stochastically you can do that just based on Bayes' theorem. And we don't want to argue Bayes' theorem here. Yeah. You had a question? Yeah?
Well, I have a question.
Yes.
Again, it's a question that I asked before. Can you train this on simulations? Because can you
Yeah.
train this on data?
No.
You cannot, because you don't have the...
No, you have the paired, you need the paired events.
Of course, yes.
Yeah, so well, I should say, I wouldn't know how to get those paired events, but some genius might come up with some way of doing that really nice. At this stage, you train this on simulation.
You have to trust our simulations.
Yes, you train this on a forward simulation, so you need one direction simulated. That gives you the paired events, and then you can train your network to learn the forward direction the same way or the backward direction. And that is the technical advantage, but you need training data and important paired events. And you need to get them.
Yeah. We have the same thing in cosmology and tabulator. We
Yeah.
train on specific, okay.
This is a very broad, like, everybody has the same problem. In science, I'd argue, right? I mean, everybody has these problems. And the use of these conditional normalizing flows, or conditional INNs, is like absolutely universal. I mean, everybody is using them right now. Like, I just I gave a lecture in Stuttgart. It's an engineering university, really, right? I mean, like, lots of engineering there. Same problem, same technique, same networks, different original authors, obviously. Like, different specializations. You look into the same thing. As a matter of fact, I'm not quite sure, but I think there was a really nice paper by Shelkoff and a bunch of a bunch of gravitational wave people. They're using this for inference of gravitational wave signals. Again, different application, certainly different details, same question. Everybody is using the same. It's the same thing. Everybody is doing it.
So another question: collaborations make the unfolding probability distribution accessible for phenomenologists?
We're working on it. So I would argue that, okay, I should say, this is my favorite unfolding method. And it's pursued by Atlas, for instance. There are studies on that in Atlas. There's another method which is based on reweighting these distributions. Again, trying to get these distributions right. Do I have them somewhere? Yes, essentially on these two distributions here. If you don't want to sample, if you're happy to just get the distributions right, which you might well be, right? Because you're just looking at a certain number of events. Then you can actually, there's an easier way of doing that. It's called omnifold. It's a really, really nice paper. Read it by Jesse Taylor and Ben Nachman on how achieving a similar, possibly the same task using reweighting methods. there are people doing this in Atlas as well. I don't know, like, I'm not an Atlas insider, like, from what I hear, I think these, like, the like, availability of unfolding is something that's going to be one of the big stories in 1.3, because now, technically, we can do this. I mean, in principle, people could do this. If you ask me, like, as a physicist, like, you know what I do for a physics living is, for instance, global analyses of, like Higgs and top sectors, and you're looking at, like, dimension 6 operators and how they're constrained by the kinematic distributions, right? Yet another one of these problems where, like, I need to reproduce experimental data, right? So in the Higgs group, what they do is they, like, give you, like, distributions, like, forward simulation distributions. They're all plotted. We know what they are, so we can try to reproduce them. But it's a pain in the ass to do because you need a fast detector simulation, and then you need to, like, reproduce them with the detector simulation, which means you tune the detector simulation, blah blah. It's quite hard work, right? It's tedious, right? Or they give you these, like, simplified template cross sections, which are totally useless, actually. Sorry. But no, we have also written papers on that. But what I'm saying is, we can do that. But the top people, the TT bar people, what they do is they give you kinematic distributions of PT and ADA and stuff of the tops in TT bar production. Everything else unfolded under the assumption that our dimension 6 operators are not going to do anything to all the stuff that you unfold, like detector simulation or top decays, which they won't, right? And now, that is brilliant to work with, right? I mean, this is, like, exactly the information, because then I just, our students, we just run MATgraph to TT bar. Everybody can do that. Like, at high precision, like, everything controlled. We know exactly, like, what TT bar simulation tool the experimentalists are using. If not, we just call up the Aachen people, and then we know, right? So, like, you can do that, and that's brilliant. So that is a sign where unfolding actually makes a very big difference. Other places, by the way, where unfolding, like, we don't talk about it unfolding, but think about parton shower. I mean, in a way, jet algorithm is nothing but unfolding parton shower. So people do it all the time. But so my, like, excitement currently in view of run 3, which otherwise is unlikely just with twice the luminosity to, like, turn up anything, like, physics-wise particularly interesting. Sorry, Atlas, sorry, CMS. Techniques-wise, I think there's a couple of really cool analysis techniques, really cool, like, technique, machine learning, and other techniques that can make all the difference in view of high luminal LHC. So even if I might not expect much new physics from run 3, run 3 is the perfect machine to try all these cool new ideas for high luminal LHC, because for high luminal LHC we will need them. Yeah? Okay, so this is just inverting stuff. And, like, I can draw, like, one figure for you, like, kind of a nice figure. Yeah. So, like this here. Imagine now you invert. I mean, you're looking at process, like, this is the one that, like, we played with is what do I have here? Let me check. I think it's WZ production we looked at. Let me check which plots I'm going to draw here, being they all look the same, but I mean, here we go. Yeah, it's WZ production. We looked at WZ production plus jets. So, like, you look for, like, PP to WZ, and you use plus jets. And, and let's assume that the decay you're looking for is, like, W goes to jet, and Z goes to lepton, and plus jets, right? And now I do a forward simulation, and I want the invariant mass of the W boson to be right. So I know how my invariant mass, my invariant mass. So this is, like, the invariant mass reconstructed of the W. You know how it looks at parton level, right? I mean, this is, like, 80.22 here, and then it looks like this. And if it doesn't look like that, well, then we have a serious problem at parton level, because it should look like this. Now, so it has a nice peak, and then it has a Breit-Wigner shape, right? Now, what happens when you apply detector effects and all kinds of other stuff, where that thing becomes a cow pie? I mean, it looks like that, right? Remember, I have a model here, right? I'm training this on paired of events, so I'm assuming that these events are actually W plus Z, like, I'm have a forward simulation, so I have a model, WZ model there, which means if I now invert, my machine learning should magically resurrect the W mass peak out of this. Right? Which, if you think about it, like, if you plot it, it looks like magic, right? It looks like, okay, you start with something that's really cool, and then detector hits. I like that noise. It goes well like with the microphone, and then magic happens, which is just encoding, like, the pattern level and detector simulations in the neural network. But, like, magic happens, and it resurrects out of, like, the ashes comes the W mass peak. Right? It works. Yeah. It's a figure 57, like, it works. Of course it works. It's just a nice way to showing it, right? I mean, I should say there is, of course, as always, there's work to do. Like, this is just a start. Things get harder a little bit because you see, it's not only do I need to get the detector effect jet here right, somehow my network also needs to decide which of the at least 2, but up to 4 jets actually give me the W mass, because at the pattern level, the invariant mass with one of those jets and one of those jets is not the W mass peak. So this resurrection only works if your network describes the detector effects right and also, like, gets the combinatorics right. And this is a well-known problem. Like, getting the combinatorics right and, like, these kind of events has always been a problem. It's a problem in every analysis. And here I should say that neural networks help, but I think the neural networks also need some help from you guys to do better at that. So the current limitation is here the combinatorics. It's not undoing the detector effect, it's undoing the combinatorics. I mean, eventually that'll work, but, like, this is something like that's the open question.
What does it mean again?
Oh, if I knew which at my hadron level, like, if I knew which of my jets correspond to the quarks that come from the W, I can resurrect the mass peak. However, if I then need the network to pick my 2 W quarks out of 4 jets in the final state, this is an extra task for the network to learn, and that's tough. And that is, like, where the simple picture here becomes a little bit more complicated. You other networks, and I think to be fair, I think we have an idea, like, people have an idea what to do, but we haven't solved that fully. So there's work to do. If anybody like in the audience wants to become, like, maybe not famous, but, like, extremely well respected, that would be one of those problems to solve. And this is, by the way, you talk to, like, Atlas and CMS people, and they will always tell you, no, this is not new, right? This has been a problem forever. Remember, if you're old enough, well, remember TD bar Higgs, Higgs BB bar, right? I started with this. TD bar Higgs BB bar, you need 4 Bs, right? Which of those 2 Bs should you try to reconstruct the Higgs mass from? Well, yeah, whatever, find them, right? Imagine, so, like, I talked about the example, I need to tag 4 Bs, but now you have 4 Bs. Okay, and now you have to decide in your analysis which of them should give you the Higgs mass. Well, I don't know. Like, look at the kinematics, figure it out. And this is, by the way, a very old neural network problem. People have been using neural networks to decide that more or less successfully, I don't know, for at least 20 years. Yeah, so this is a problem, an additional problem. Okay, now we can unfold. Unfolding is not really inference, right? I mean, unfolding is fine, but it's not inference. What I want is, actually, I want to go a step further, and I want to yet again change this. Like, so I want a network that takes the, I can do this on this picture, that takes this kind of conditional approach, the conditional normalizing flow. And if you're, like, a proper, like, analysis person, you want, I need that, and I need that, and I need this, and I'm missing a hand because I don't want to get this wrong. So what you want is, you want your condition to be something observed. So this is an observed, that's what you call it, events, whatever, right? Observed events. Right? What you then want, you want your random numbers to be mapped on a model space, right? So these are my models. Model simulations. So that you have a model parameter here, and you basically train your network to generate the probability distribution in model space given an observed event. Now that's inference, right? And that's, if nothing, that's definition of inference, right? So what you want to use a generative network. This is like, again, a generative network, not like, some kind of a regression network. You want a generative network trained such that you give it some kind of an observed event, a bunch of a jet, right? Or you give it like, a shape of a gravitational wave signal, or anything you want, right? Something that you observe in astrophysics. Our colleagues in Heidelberg, Ralph Klessner and friends are doing this for astrophysics, the same thing. You want some kind of observation, and you want your network to map random numbers which you throw into a distribution in model parameter space. Which, by the way, that's a Gaussian, right? By definition. That's not Gaussian, right? That could be anything. Right? I mean, probably a single mode, but this could be any kind of distribution. So that's proper inference. So same architecture, conditional INN for inference, right? All I'm doing is I'm now replacing my pairs of events at the parton level and at the Rico level and the parton level. I'm replacing them with pairs of simulated events of some kind, and as a function of model parameters and then the underlying model parameter. So for instance, what we did is very simple, a simple example, something that I have liked for a very long time. I'll give you the example that we played with, and then you can, you find in the literature a million different applications. But here's my favorite particle physics example for that. And that is, remember that splittings of jets, parton splittings here, they're blue ones. These two splittings here that we typically write down. These two splittings are functions which you can write down as splitting kernels. I can do that, but I can also skip it they're plotted here they're shown in equation 526, except I probably changed it. But this is on page 99. The most important leading aspect of these two splittings is they come with different color factors. CF, we call that the 2 Casimirs CA. Or for QCD, 3, and that is 4/3. Oops, n squared minus as well. It's n squared minus 1 divided by 2n, which is 9 divided by 6 is 8 divided by 6 is 4/3. Yes, okay, good. And that's n, and that's 3. Okay, now we got it. So these are the two color factors. And I don't know why, for absolutely no good reason, one of my favorite measurements people did at lab was measure these things. They actually measured. They're measured to be, from lab mostly, they're measured to be 2.89 plus minus 0.21. And this one here is measured to 1.30 plus minus 0.09. And I would argue that the same way that we are rephrasing the measurement of the Z-width as a measurement of the number of light neutrinos, this is actually the measurement of NC as in QCD NC, number of colors, right? And since you measure both of them, it's actually a believable measurement. You also see measuring it from the fundamental and the adjoint representation, so it's nice. That's a serious nice measurement. And you're wondering why could the LHC not do anything like that, right? Because if we have anything, we got jets, we have jets, and we can simulate them, and we can simulate them with Sherpa. So essentially the question is, I have a bunch of jets. Can I measure these splitting functions at the LHC? In principle, I can, but remember how jets looked, right? You have seen, I showed you, jet looks. That's a jet. Or two jets. Yes. Or you're missing shit here, stuff. You're missing things. Like, this is a jet. And so that, it makes that problem look a little harder, right? I mean, you have a bunch of calorimeter entries, and the jets, these splittings describe exactly the difference between these two things and one of them, right? And this is kind of convoluted problem to solve. And so this was my favorite problem. So this is a problem where I said okay, I'm sure we can do this, except we need a good technique to do that. And this is our little example that we used for this. So what we do is we simulate jets. Our model parameter space is exactly, for instance, CA and CF, or other properties of the jets, right? Exactly CA and CF. We simulate jets. So let me remove the yellow and say exactly what we're doing here. So these are. So forget, this is Sherpa, we're simulating. What this whole thing is at this stage simulating. We're using Sherpa to do jets, right? And we also use Sherpa to have CA and CF here included. These are model parameters, right? This is two-dimensional. Okay, no, this is actually also Sherpa. It's the same simulation here. That is CA and CF. And then I train my network, and in the inference phase, I take that network as it is. I give it a jet as a function, an actual jet as input, and I get a distribution in CA and CF. By the way, I get that for every single jet. I get a posterior probability for every single jet. I can also do that for a sample of jets. I can train the whole thing not with one jet, but with many jets. Then you get the posterior distribution for many jets. And then you get distributions like, do I have one for you? I mean, they all look the same, but pretty much. So what you get a distribution, this is a two-dimensional problem. You get a distribution. And we haven't done the measurement because we didn't get to it. But you get some kind of a two-dimensional distribution. So this is CA and that is CF, right? CA is around 3, CF is around 4/3. And then you find a distribution, I don't know, it's probably let's just assume this is somehow correlated because things are always correlated, right? Correlated. And then you can project this, or you can, in that case, this is a posterior probability, so you want to marginalize it on these two axes. So you want to do this, marginalize this on the CF axis, and you want to marginalize this on the CA. So there's a CF here. On CA, you get these kind of distributions, right? I mean, this is what you get. What's important, you get a multidimensional thing. You get pretty much something the kind of measurement that you get at lab. From a set of observables, which are really not easy to interpret, right? And the moment you run this through a bunch of high-level variables, you tend to lose information. You don't want to do this. So this is what would be one of my favorite applications. But again, you find applications of this stuff all over the case, all over the place. Now, in our case, this architecture has a name. It's called base flow. And for once, this is actually Bayesian. Why is it Bayesian? Because I told you that you're training these kind of your network on pairs of events, or here you would be jets and model parameters, right? And what you get out is a posterior probability distribution. Now, imagine you have a bunch of jets, and you have a posterior probability. They don't factorize. The posterior probabilities, unfortunately, don't factorize. Likelihoods factorize. Probabilities don't factorize because of normalization. So the disadvantage of this model here is that, the advantage is you get a posterior probability distribution. The disadvantage is that you don't have a factorization, so you cannot train this on a number of 100,000 jets and then run it through 200,000 jets. Because, what you need to do in Bayesian language is you run it through the first 100,000 jets, then call the posterior the prior of the next measurement, run it through another 100,000 events. So that's Bayesian construction, right? I mean, that's actually how it is. So you could do that, but so this is actually Bayesian because it gives you not a likelihood, but a probability distribution. And we're thinking about it would be nice to get a likelihood out here, so it's for our purposes in particle physics a little bit easier to deal with. So this is why it calls base flow, but really everybody is doing that.
So has this been done for jets in Heidelberg?
No, no, it hasn't.
It's very difficult.
I'm not sure how difficult. I mean, in principle, we could do this on CMS open data if we wanted, right? If we had the time and the students, and if the CMS open data was in any way, like, how to say, like, documented in a way that one could actually use it for something like that, like, you could. So, like, if you have, like, what is it, the deal with the CMS open data? I think if you're CMS, you can't work on the open data, right? I think, so what you need is, like, you need an Atlas student who is good friends with a bunch of CMS people. They can call up and say, like, here, I need to know how this is done, and then kind of work on the open data. And no, I think then we could do this.
It's more complicated because not only CF and CA that are the free parameters, you have all the nuisance parameters that you have to take into account. So it's much more complicated.
Yeah, it is, but I think on the scale of things, jets are relatively easy objects. So, like, you're right. You would probably go for, like, a PT range where we're relatively sure that all the calibration is right. You see, the nice thing about jets is that there's tons of them. So you can actually zoom in on a phase-space region, on a jet size, where you're sure about your calibration, where everything works, where then nothing is funny is happening with the jets. Like, events, it's always a little bit tricky, right? But so you would probably go to, I don't know, you would go to a nice jet size where, like, you don't have, like, big problems with, like, pile-up stuff, so that would be relatively small jets. You adjust your PT range such that, like, you don't have stuff flowing out, like, yeah, so it would require some tuning to do, but yeah.
That would be great.
But, yeah.
I would be very interested.
Yes, anybody, like, wants to do this. It's like, I mean, yeah, in principle, this is not that hard. I mean, the technique, like we've done, like, you can do this. And of course, there is, like, if you think about these, the splittings. I'm also, by the way, done with my lecture. So I've run out of material that I really wanted to cover, and I think it's bad style in the last 20 minutes to start something completely new and race through it like hell. So we don't do this. But, like, just to give you an example, like, what you want to do with this. If you want to do better, it's, of course, the splitting kernel for glue to glue, right? Actually, the form is, it has a CA here, and then it has a term that goes like, that's actually in terms of momentum and Z, momentum fraction, and Y is the reduced angle, right? So 1 minus Y divided by 1 minus Z, 1 minus Y, plus things mirrored in Z. 1 minus, so this is just 1. Z, it's always symmetric in Z, and 1 minus Z because it's like, a glue or two glue ones. Okay, so this term here, that term is the divergence. That's the leading term, like, this is what describes almost everything, like, so, like, we call this, like, divergent here, a D, or D glue glue, right? Then, it has a finite term that you can calculate, right? So this is just the collinear, soft collinear divergence, and it has a finite term that actually in the SAM model in QCD has a simple form Z times 1 minus Z, and you can call this FGG, right? And then it has, like, PT suppressed terms, which we don't know. I mean, some of them we actually can calculate, but in generally they're typically not included. So, like, there could be, like, constants, CGG. And let's assume they're explicitly suppressed by PT, and PT in these coordinates is YZ times 1 minus Z. So if you think about it, what you want to test, if you're at it, right, you actually have, like, 3 terms. You want to see, first of all, the pole is right. Well, the pole is going to be equivalent to CA. It's the leading term. That's the one, right? Then you can check if, like, generations of physicists have screwed up the finite calculation for the finite number here. Actually, it's not that simple. Like, think about it. The fact that we calculate we can write it that easily is that we always assume there is only 1 to 2 splittings, and we know that that is not the case. Right? We don't have uncorrelated 1 to 2 splittings describing a jet entirely. So maybe this approximation will already hit in the extraction of FGG, where you would find that the terms that, like, you're ignoring, like the effects you're ignoring, actually already, like, are visible at that level. And then you can, like, determine the rest term, because that is a deviation from 0. That's what we assume that to be 0, right? And then you can check how big that one gets, right? So you could check, well, you can reproduce CA. My best guess is that we got that right. You can see if there's like, something big, like reasonably big, happening in the jets, which is like exactly like, what Gavin Salam, for instance, they're calculating, right? They calculate exactly these effects. And you could check, are they big enough to like, affect FGG, or are they like, part of the restrum that like, comes with PT suppressed 1-to-2 splittings? I don't know the answer, right? You can do that. So like you can do these measurements. So this is like, just the first step. You can, right? And point is we have enough jets. I mean, it's not going to be a shortage of data, right? At some point, some systematics is going to kill you, as always, because if you have too much statistics, systematics is what is your concrete wall. Good. Yeah. Sorry, we are 15 minutes early, but questions? I figured maybe a little more coffee. Then
We have ample time for questions.
What did he measure exactly at lab? So where are these numbers coming from?
this one here is essentially it's event shapes and jet shapes at lab, at the plus and minus. So essentially jets, but they're actually, this is like essentially correlators of jets. Well, correlations between jets, and then, like for instance, 2 to 3 jet rates and stuff like this, where this enters in the collinear range, and then also kinematic observables, like inside the jets. I don't know. They all have names. I tend to forget them. But it's essentially, it's a super nice. I mean, read it. It's a super nice analysis of lab data. The Munich guys did that. Really beautiful. And I think, by the way, if you ask me, like, okay, 3 neutrinos, fine by me, right down there, but number of neutrinos is something that, like, okay, like, this, but this is non-abelian gauge groups, and, like, non-abelian gauge groups beat number of neutrinos, if you ask me. If you want to measure 2 3s, I'm all, like, for the non-abelian gauge group. It's just cooler. Okay, sorry. Yes.
So in the long chain that you have been writing down from the Lagrangian going to the final detector event, I mean, there is the elephant in the room, this hadronization in the middle that basically no one knows how to do it correctly, as far as I understood, or to estimate an error. Is there some chance to do something about that with neural networks?
Well, first of all, yes, no, it's not. First of all, it's not the elephant in the room. It's the elephant in the room after, like, we have solved all the other elephants, right? I mean, yes. So I don't think of it as the elephant in the room, because if you think about it, in the days of lab, like, every bloody point in that chain is an elephant, right? It just, we have pretty much solved them all to the precision requirements. And this, by the way, that is behind the success of the LHC, right? Like, when I grew up, everybody says, like, hadron colliders are just for discoveries, electron colliders are for precision. This is bloody nonsense. I mean, this is absolutely not true anymore. Or, like, as a great physicist said at the CERN, at the DESY when I was a student, at the DESY seminars, would always, like, say when somebody said, like, that we can't do this, he would raise his finger and say, well, that depends on how smart you are. And he was not very popular with his colleagues. In any case, so so like we have solved all of the other problems, and we are solving the fragmentation part, the hadronization part as well. But these are like this is a list of elephants, and we need to solve them. And the next one is always the elephant in the room. And in that sense, you're right. Hadronization is not that it's not understood. There's a young man in the room, like, spent his PhD, like, trying to understand that. Because if you think about it, it's actually not that complicated, the problem, right? It's essentially a bunch of spectra, and some of them we can calculate, and some of them we cannot calculate. But if you think about them, it's really a combination of, like, Breit-Wiegeners and continuum spectra, right? And then a lot of decay spectra, right? If you look at, like, the amount of data, like, there's a lot of data, like the pre-LHC on that. My best guess is if you looked at, like, cutting-edge LHCb data, you have actually better data on heavy flavor, like, fragmentation. So in the sense, the theoretical description is not super complicated, and there's enough data. So that screams machine learning, right? I mean, it's just it's just a very complex yet not super hard individual, like locally super hard problem. Screams machine learning, and people are working on that. I mean, there's groups like there's more like hadron collider and more like hadron physics people working on this, like Berkeley, for instance, like they're talking about this. In Cincinnati, there's a group like thinking about how to model this with machine learning. It'll be solved. It'll be solved. I mean, it requires some work, but to me, it's like if you have the physics knowledge to do that, then it becomes a classic complexity machine learning problem, as far as I'm concerned. And this is why I think it's the next big task. But you see, calculating the partonic cross-sections like to extremely high precision, that's different. Like this is like you can like through a lot of machine learning and trying to guess like n cube LO corrections to Higgs plus 2 jets. It's not going to help you, right? So like it's very it's like you need the theory calculation. Hadronization is really something that you can probably do data-based with methods that allow you to accommodate the complexity. It's my guess. So don't worry. People are at it. They have the right toolbox. It'll work. Uncertainties, by the way, you're completely right. But this is Peter's thesis, right? I mean, it's not that hard to assign uncertainties to hadronization spectra. I mean, these are just fits. I mean, all of these things are like fits of spectra. Just don't throw them away, and then you have them. Right. They tend to be thrown away.
More questions?
So this thing here, is it similar to the art AI, whatever the name is, that it's doing a similar thing? You feed it enough Van Gogh that at some point it can create an actually new Van Gogh or Picasso or whatever?
Yeah. I mean, but that's always it. So the original Van Gogh, the tool is called Gango, right? Obviously, because it's a GAN. If you look at some of my earlier talks, you will see, like the more colloquium-style talks, I show some of those. As a matter of fact, there is the first piece of art generated by a neural network is a portrait of Edmond de Bellamy, I think he's called. It's a portrait generated by a neural network, by a GAN actually. And it's trained on portraits, and it's a new portrait. It was sold several years ago for $432,000. The artist signed with his or her loss function, appropriately. So these generative networks are exactly this, and I think it is important. The things that I want to do is exactly that. I don't want to map spaces. I want to sample, and sampling means new. Mapping spaces means reproducing structures. And this is, I think, that's exactly your point. In that sense, yes, it is exactly this. But most of these art things, and also, I think, Veronica Sun's paper, and also, I think, Jesse Taylor's paper, they're all working with GANs, not with flows, if I remember correctly. Because that's a field where maybe uncertainty estimation is not your main problem. Right? I mean.
This is a Van Gogh plus minus. Okay.
Yeah, so.
I can ask a metaphysical question.
Oh, beautiful. Love those.
So our field, as you mentioned in the beginning, is blessed with very high quality data. And in principle, the explosion of machine learning in all sectors of industry and science does not have our wide variety of high quality data. So at what point do you see an effect from, say, poor quality data or sparse data or some level of a weak chain? So I can, what work can we do stuff that's cool that other people can do that we can do? First of all, so we have two things. We have high quality data, we have full control, and we have this precision simulation chain. So if you think about everything I talked today, it requires a forward simulation. And if your simulation is not good, what's the point of applying it to data, right? I mean, if you already know
that your simulation doesn't agree with the data, well, then forget about the inference part, right? I mean, it's not going to fly. So, so everything I said today, I would argue that, like, you know, our field is like potentially, like, you know, in the situation to lead stuff. So like, if you look at the other applications, as I said, in gravitational waves or in astrophysics, what they do is they use these kind of, like, you know, neural network inference techniques for, like, you know, well-defined parts of their generic problem. Like, you know, they have like a certain tasks and for which they do have those simulations, and then they can actually do this kind of stuff just like us. We can do this and full blast. We can, like, you know, everything, including, I mean, even our hydrogenization models are good enough for that, right? I mean, we can actually do these kind of inference things for everything. And, like, you know, I can, just an anecdote here, that we wrote our base flow paper that was talking to a bunch of people in Heidelberg. The original author, by the way, of base flow is Stefan Radev. He's a psychologist. Like, he's not a physicist. But we basically, over coffee, they say, oh, we can do this. And we said, OK, well, give it. We want that. We want, like, Tilman wants to measure CI and CF, right? I mean, so we want this. Give us that data. So then we have these CINN tools. And the CINN for unfolding, for instance, this, like, you know, the original paper like that we wrote, has all these, like, you know, original authors on the paper, as does the base flow. And the reason why is that they submitted their ideas preprints before we submitted our papers, but our papers got published before the ideas preprints were published, because the ideas people in the community, the machine learning community, said, oh yeah, that might be useful and blah, 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 blah. And like our physicists looked and said, like, yeah, we want this, like paper published, like go, print, right? I mean, so yes, I mean, like, you know, if you think, like, you know, about these kind of methods, inverse simulation method, these kind of things, it is extremely easy to convince, like, our experimentalists and everybody, like, this is relevant, interesting, and also worth putting time and effort in. In the other fields, it's, yeah, you can solve certain problems, or in a broader field, I mean, people just might not care that much, right? Of course, then, when you become, like, more, like, you know, you're more general, and you say, like, no, but this allows me to generally solve inverse problems, like, you know, stochastically defined so inverse problems, then they get interested again in that again from a more formal perspective. But, like, you know, if you want to convince people to use these methods that I talked about today, I think, I mean, it's a very easy use case for particle physicists. So I think what you'll see is a lot of these things come out of Run 3 and particle physics and related astrophysics, right? I mean, they're all friends, right? They're using the same tools. They're, like, you know, students talk to each other, right? And this is, so, like, you know, things will come from there. And that's going to be much more dynamics than in the general field of machine learning relative to other applications. So we can push it. And then this, and the other thing is, I should say, like, you know, all this, like, construction, like, you know, of, like, you know, how do I do like a reliable precision generative network? I mean, we are the people who do that, right? I mean, like, and I'm not talking me. I'm talking now Sherpa, Matgraph, Pythia, Hervik.
Anything else? Okay, well, we'll thank Tilman.
Yeah, I need to say one thing here to the young people in the audience, right?
Go ahead.
Everybody, especially those like model builders from CERN, everybody is always telling everybody, like, you know, that, like, you know, we are a field in crisis, blah, 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 and we're extremely depressed because nobody has found my favorite model. And I know this has an effect on our young people because for some reason they believe that. And I just want to make sure that you know that this is total nonsense, right? I mean, we are a field where model building is in a state of deep crisis because we have not discovered any of the models that people like me like dreamt of like discovering. But, like, you know, this kind of stuff that I'm showing you here, like, you know, this is the physics program of the High-Lume LHC, right? This is, like, you know, forget about the models. We'll find the models. If they're there, we'll find the models. This is, like, you know, a very, like, you know, data-driven, like, you know, but also, like, you know, innovation-driven field. So, like, you know, and, like, work at it. Like, you know, this is not how a field in crisis looks, right? I mean, we have lots of data, we have lots of questions, we have great tools that we're developing to relate the two to each other, right? So, like, don't listen to anybody who says it's like all like particle physics is down, blah, 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 right? I mean, we're not, right? We are actually in pretty good shape. We are doing, like, you know, like exciting stuff based on big data sets. very similar when it compares to the cosmology, right? I mean, cosmology is the same, right? I mean, they also have not discovered like, new particles recently, right? But like, again, interesting questions, big data sets, lots of stuff to do, right? I mean, just like, let's go after that and like stop listening to the people who tell us that's a field in crisis. And this machine learning stuff is great because you can bypass all the old people like my generation and me who like think that we're in field of crisis, and while we're sitting in our office depressed, you can just like do cool stuff and pass us and get a faculty job somewhere and like, laugh at us. Yeah, please do that. Okay.
On that note, let's thank Tilman.
Thank you.
So we'll see you after the coffee break for Raffaele's final lecture.